Okay, so we are looking at production systems. Which is a form of forward chaining or forward reasoning, and in particular we are looking at algorithm called Rete algorithm, which uses the Rete net as a structure, which is what we were looking at. So, what I want to do is to show you an example of a Rete network today, but just to make sure as to what we are talking about. So, remember that the production system, the basic idea is that we have a 3 phase cycle, we have match phase, and what the match phase does is takes rules as input and data or facts as input, and it produces a set of rules which are matching with data, and we had called that set as conflict set. And this set is given to a phase called resolve, which selects a rule from the conflict set, which is given to execute. And what execute does is produces either a positive token or a negative token, because we have said that you are allowed to delete statements in your knowledge base essentially, and then these are fed back into the network essentially. The basic idea of a Rete network was that instead of doing this match all the time, which we saw was expensive, we want to do it once in the start, and after that any changes in the working memory or changes in the knowledge base, we want to see that what changes are induced in the conflict set essentially. So, the working memory, we had this notion of working memory. So, the facts are in working memory, and these are called working memory elements, and typically it may look like this, that there is a student. So, there is a class name. So, just think of it as an object or something which comes from a certain type essentially. So, a student is a certain type, and then you may have attribute and values. So, you may have attribute called name, or you may have an attribute called marks, and so on essentially. Now, what the Rete algorithm does, so just to recap, you start by entering a working memory element in the top, and at each node you ask a question which will tell the system as to which what is the working memory about essentially. So, for example, at the topmost level there might be a question like what is the class name. Okay. So, for each class that we have in our knowledge base, so for example, student may be here and some other kinds of data might be there. So, if we see a token which is of the type student, then it should come in this direction, which is here essentially. Then we may ask some other question essentially. So, for example, we might ask something like marks greater than 60. Then what would happen is that whichever are the tokens which have marks greater than 60 would go down the left branch, and the others would go down the right branch essentially. So, the top half of the network we said was a discrimination network, which basically separates the data and sort of directs it towards its rules that it is going to match essentially. So, these kind of nodes were alpha nodes, and then there were beta nodes which basically pulled in data that a rule requires, and essentially supplies it to a rule and says okay, this rule has the matching data essentially. So, that is what we had looked at in the last class. So, today we will look at an example first, and then depending on how much time we have, we will look at the language itself in a little bit more detail and what it allows us to do. So, I have sort of copied from my book some example, which so I will not write it all over again. So, we will essentially discuss it with a pre-written piece of data. So, let us say we want to write a small program to recognize or classify geometric shapes essentially. So, we may have things like pyramids or cylinders or vands or domes. Let us say we have 4 kinds of objects which are described using certain attributes and values, and given our knowledge base we want to identify how many which van we have, which pyramid we have, and that kind of stuff essentially. So, for example, a rule for identifying a van, as you can see in this red page here, says that let us say every block has a name. So, we want to classify a block. Block A is a van, block B is a cylinder or things like that. So, the rule for van says that the base of the block must be circular with an area of size 1 in some units. The side of the block is curved and tapering with, and it has color black, and the top of the block is a point. If we have a block of this type, then call it a bond essentially. So, let us say we have these 4 rules. So, there is a rule. So, here are 2 and 2 on the next page. So, there is this rule called a green pyramid rule. So, we are talking about a green pyramid obviously. So, the first, now each of these things that we see here, these are the 4 patterns that this rule is looking for. This is the antecedents of the rule essentially, and each of these patterns is describing some working memory element which starts with a class name. So, we have class names like block and base and side and top, and then the attributes and the values. So, remember that the thing with the hat is the attribute name, and following that is the value essentially, and remember that something like this is a variable. Anyway, this is too thick to write. So, this is a variable. Anything in angular brackets is a variable essentially. So, the first rule says that I must have in my knowledge base one working memory element. So, these are working memory elements, remember. So, this is working memory element 1 or pattern 1 and so on, whose name is block, whose type is block, and it has an attribute called name which has some value x. Then the remaining 3 patterns must have somewhere this same value x. So, wherever we repeat this x, they must have the same value essentially. So, that is the whole idea of sharing a variable. Then the second pattern says that the type of that working memory element is base, and it is, we are talking about a block whose name is x. So, we are not naming it x, but the attribute name here is block, whose shape is square. Now, this square is a constant, it is not a variable because it does not come in angular brackets. And then we are allowed to do things like logical tests whose area is greater than 1 essentially. The side of the block has angle less than 90, the surface is plane and the color is green. The top of the block is pointed essentially. So, if all these conditions are satisfied, then we say that we have a pyramid, and we can The right hand side of this is our action. So, we are saying we make a class block X type green pyramid essentially. So, we are not really bothered about the right hand side here, we will maybe in the next class we will see what is the kind of actions we can do. So, likewise the second rule says, which is a cylinder rule which identifies a cylinder. So, the three things, the second, third and the fourth patterns are important. The second pattern says that its base is circle and area must be greater than 1. The third pattern says that the side must be of angle 90 degrees and the surface must be curved, and the last pattern says that the top must be the surface must be flat, as opposed to a point, which was the case for a pyramid or a wand essentially. So, I want to show how I will show you 2 more rules and then how those 4 rules, what is the Rete network that we construct essentially. So, the Rete network is basically a compilation of rules, it has nothing to do with data. The moment you have decided a set of rules, then you have a Rete network essentially, and that is why Simon and Newell they called it long term memory. It is the kind of knowledge that a problem solving agent has essentially. So, the third and the fourth rule are the Vaughan rule and the Dome rule. I have colored the Vaughan rule in red, because when I show you the network, you should look out for the fact that these 4 patterns that are needed for this rule to match, what are the paths they will take in the network essentially. So, and those paths I will show in red. So, you must remember what the Vaughan rule is, and then we will see how it shows up in the network essentially. So, the Vaughan rule is similar. The first rule is the first in all these 4 rules is just simply says that we have a block called some name essentially, just identifying the block. The second rule says that the shape is a circle and area is 1. The third pattern says that angle is less than 90, surface is curved and the color is black. So, let us say bonds are always black, and the last one says that the surface is a point. So, likewise we have a dome rule. No, you might have seen the Sanchi stupa or something like that. It says that the base is a circle of area greater than 1, the side starts with an angle of 90, but the surface is curved, and the top is a spherical surface essentially. So, that is something that we would call as a dome. So, we construct a Rete net for the rules above. So, this is basically I have just copied from a book. Now, the important thing is that there is no unique Rete net corresponding to a set of rules, because essentially what you want to do is to test for various conditions, and you could test them in any particular order essentially. The goal that we would have is to minimize the number of tests and to make as small a network as possible essentially. So, you could choose any test in any order and construct different networks, and you could also combine beta networks in any order, because each of the rules that we saw had 4 patterns. You could combine 1 and 2, then 3 and 4, and then the combined patterns in any particular order. The objective would be to share as much as test essentially. So, if the different rules are testing for the same thing, in our case for example, the first pattern is always the same, then you must, for every working memory element, you must apply the test only once essentially. So, once you construct the network, we will also insert these working memory elements into the network to see how it works. So, the working memory elements or the data, so each of them is like a record in a database, you might say essentially. The first one says I am talking about block, the base of block A is shape square and area is 20, base of block B is shape circle, area is 20, and so on and so forth essentially. We want to see that given this data, which of those 4 rules match essentially. That is our main interest at this moment essentially. So, here is a okay. So, the numbers on the left that you see here, these numbers, these are timestamps, and we will see later in another class that timestamps can be used in deciding on what is the problem solving strategy that you are using essentially. Otherwise, they are of no interest to us at this moment essentially. So, the numbers on the left are recency numbers, which is what this community calls it, stating the order in which these working memory elements were created. They are used to identify the working memory elements in the Rete net. So, we will identify in the diagram that we will draw each such element by its recency number or timestamp. So, that we do not have to write the full thing there, and we will see that some tokens will get combined in beta nodes. And then finally, we will see in the network that there are 2 rules which are matching with this data essentially. So, here is a network. Let me enlarge it a bit. I hope you can read it. Is this legible, or should I enlarge it a bit more? Is this fine? Okay. So, you can see from the top, the root is where the token comes in, and the red lines are the ones which will match, which basically show you what are the patterns that we are looking for, the bond rule. So, it needs 4 patterns, and these all 4 of different type essentially. So, you can see that the type of this thing here, the class is here the class is a base, here the class is a side, here the class is a block, and here the class is a top essentially. So, straight away we can see that tokens of different classes will go down different paths of the tree essentially. And then we have tests like so, if you look at this class is equal to side part here, you can see that there is a test which says angle is less than 90 and angle is equal to 90. Now, how did we arrive with this test? We arrived at it by looking at the 4 rules. There were 4 rules, some of them wanted angle equal to 90, some of them angle less than 90, and therefore, we have only these 2 tests essentially. If there were other rules stating that, for example, if there was a block which says that the angle is 45, then we would have had a third branch essentially. The branch. So, this network is created by looking at the rules essentially. So, it is a compilation of the rules in some sense essentially. So, for each thing we have, you go down and you have another test, you go down you have another test, and so on. And then the blue nodes that you see here, these are the beta nodes essentially. They are accepting 2 tokens and combining them together essentially. So, the numbers that you see in gray, can you see them, or? Yes. Okay. The numbers that you see in gray, for example, this number 7 refers to the working memory element number 7, and it has come up to this point, and it is not able to go down any further, because it is probably looking for to go down further to this beta node here. It needs a matching element to come from the other side, from the other branch, and only when the matching element comes will this working memory element which is stuck at this place go down to this circle node here, and then we will have a combined pair of tokens essentially, and this process will continue. So, essentially when 4 tokens come and meet at a point, because in our example each rule had 4 patterns. So, once 4 tokens arrive, then a rule would be ready to fire essentially. So, which is happening, as you can see. So let us look at the bond rule. So, I wonder whether you remember the bond rule, but essentially these red lines are the bond rule. So, area is 1, base the shape is circle. So, the area of the base is 1 and the shape of the base is circle. So, this branch that you see is talking about the base essentially, and it is a block whose name is x. So, this x is essentially we are using simply to say that we are talking about the same block essentially. So, if there is a block named A, then it can only combine with another block named A which is coming from a different direction. So, that x is equal to x must match. That is what this beta node is doing, that if there are two variables which have the same name in the two branches, then they must match the same value essentially. So, the Bond rule will have that. Then another thing will say angle of the side, if you remember, is less than 90, the surface is curved, the color is black, and of course, the block has a name which must match the other one. Then there are two more patterns which are coming. One is that the class is a block whose name is x, that is the simplest pattern which is there in all the 4 these things. And the fourth pattern is that the top of the Bond rule, the surface is a point essentially. So, that is the only thing. So, if you see that 4 red things, they first meet at these 2 nodes to form pairs of 2 tokens, and finally, they meet at this node to form to say that the rule is matching essentially. Now, as it happens with this particular data, we do not have 4 we do not have 4 matching pieces of data or 4 matching working memory elements, but we have for the green pyramid rule, as you can see here, there are 4 elements. So, x is equal to a in all those 4 working memory elements. If you were to look at the working memory elements 1, 5, 6 and 11, their name is a, they are talking about a block which is called a, and all the tests that the pyramid rule says that the side is sloping and must be green, and all those tests are satisfied. So, those 4 tokens arrived here, and now they have formed this token, and this rule is now gone into the conflict set essentially, which means that it is ready to fire. Likewise, we have another rule, the cylinder rule, which has got 4 pieces of data, which is number 2, 9, 10 and 12. For that x is equal to b, and all the conditions for a cylinder, that the base is circular, the side is perpendicular or the angle is 90 degrees and the side surface is curved and the top is flat, all those conditions are met by those 4 things. So, we have these 4 things which come into the conflict set essentially. Now, once you start the process, for all the data you would produce a conflict set. What is a conflict set? A conflict set is a rule name. In this example, the rule name is the green pyramid rule and the 4 pieces of data which come with it, which is 11, 16 this thing. So, this pair of rule name with matching data will go into the conflict set. Now, it is possible that in your database there might have been more than one green pyramid and there might have been more than one cylinder and so on, in which case you would have 2 instances of the same rule which is firing essentially. So, this is the basic idea behind the Rete net, is that the top half separates the data and the bottom half assimilates what you need for a rule to fire essentially. Now, as I said, rule based systems have been used extensively in what we sometimes call as, or used to call in the 80s expert systems. Now, we just call them computer systems. So, one of the first such so called expert system was a system called XCON, also called as R1, and it was a system which was used to configure DEC PDP systems essentially. So, essentially if see in those days computers were not like PCs nowadays, you can't go and say okay, I just want to buy a MacBook Pro or something like that. You have to practically configure the whole thing piece by piece, and it required a considerable amount of expertise, and individuals of course did not buy machines, it was basically organizations which bought machines. So, here is an example of a rule which is used by XCON. So, this XCON was a forward chaining expert system essentially. It uses the Rete network based software OPS5 to implement the rules, and this rule as you can see is a English translation of an XCON rule, and I have taken it from a book by Jackson called Expert Systems, which was published in 1986. That was the time when expert systems were very popular. The idea behind expert systems was that you want to catch a domain expert and extract that domain expert's knowledge and put it into the form of rules into a system essentially. And this whole process was called knowledge acquisition. So, and they had whole kinds of protocols of how to do that. They would have said this is how you must interview an expert and so on and so forth. So, this is a system to configure computer systems, but there were other very popular systems. There was a system called Prospector. So, you must look this up on the web or something, which was used to find places to drill for, I think, oil or minerals or something like that essentially. Now, drilling for oil is a very expensive proposition. To drill a hole costs lots of money essentially. So, if you want to drill a hole, then you better do it at a place where there is a good chance of getting oil essentially. And Prospector was a expert system which was also built along these lines to explore for geological exploration essentially. And the good thing about such things is that even if they sort of save you from one bad drill or point you to a one good drill, then they have kind of paid for themselves essentially. Developing is done by a few people over a period of time. There was another system called Mycin, which is also quite famous, which was used to diagnose pulmonary diseases essentially. So, essentially again the idea there would be to catch a doctor who is an expert and find out, okay, what are the symptoms which point to this and so on and so forth essentially. So, the whole idea of rule based expert system was to get the knowledge from experts and then put it into the system, and we will see in the next class how it really operated. We have looked at the match part as of now. We have not looked at the resolve part, which is really another key to this whole thing essentially. So, this rule says that, for example, I will just read it out, and if it makes sense to you, the most current active context. So, you are trying to structure your rules into context. So, for example, initially you might do something. So, if you are building a house, for example, you might say, okay, you want to first build the basement or the foundation, then you have to build the walls, and then you have to build the doors and the windows, and then you have to build the roof. Each of them is a separate context, and essentially you would want rules which are relevant to that context only to come into contention, and that is done by explicitly saying that this is the context. The context is building foundation or building wall or this thing, and you would set the context as part of the program running. It would say, okay, now the context is to build the foundation. Then after that is finished, then some other rule will change the context and would say, okay, the context, change the context to building walls or something like that. Then all the rules which are in the context of building walls, they would come into the match, into the conflict set. So, this is just to make the whole process a little bit more efficient. Then there is a single port disk that has not been assigned to a mass bus. There is no unassigned dual port disk drives and so on and so forth. There are a set of conditions, as you can see, about 6 conditions are there, and then you say that assign the disk drive to the mass bus essentially. And XCON or R1 was full of such rules essentially. So, the high level task breakup. So even that follows an algorithm at a certain level of detail. So, and we saw that the algorithm is controlled by deciding what is the context and things like that. So, the high level task breakup for XCON is as follows, that you check the order first, inserting any omissions and correcting for any mistakes, configure the CPU, arranging components in the CPU and the CPU expansion cabinets, configure the Unibus modules, putting boxes into expansion, this thing. So, this is how XCON was designed to configure a system. So, do the first step, do the second step, do the third step. You can see that at a very high level it is like an algorithm, and it is a very generic algorithm. It is not precise enough to say what is actually to be done. So, what XCON contains is XCON fills in the low level details of the above algorithm by selecting and firing specific rules essentially. So, I have taken this example from my book, and there of course, as you saw I have taken one example from Jackson's book essentially. So, in the next class we will try to look at what is the language. We have not really specified the language, we have vaguely said that there is working memory and there are rules. In the next class we will look at the language and some of the issues which go into building such systems essentially. Okay, we will stop here.